this all together, and we're even going to go a little bit further. So we're going to find all critical values. I'll go through both first and second derivative tests. We're going to find inflection points, and then we're going to try and put it together and sketch the graph. So looking at this function, h of x equals x squared minus e to the x, I'm actually, since I know I'm going all the way to graph, I'm going to think about domain right away. This is also not a bad idea anytime you're doing first and second derivative tests, because if a number is not in the domain of the function, you don't want to include it as a critical value. It is good for sign charts, but it's not a potential max or min. Okay, so the domain of this function is actually all real numbers. This mix of polynomial and exponential sometimes messes with people, but you can square any real number out there, and you can raise e to any power. So there's nothing in here that's going to give me domain problems. If you're really thinking carefully, you might think about the fact that e to the negative x is the same as 1 over e to the x. So we do have a denominator, and we should worry about having 0 in the denominator, but e to the x never equals 0. It has an asymptote there, right? We always get out positive outputs for e to the x, so we don't get any trouble there. Okay, first step on first and second derivative tests for both is always find the critical value. So it doesn't matter which one you're going to do, you start with critical values, which means we need an h prime of x, and this is a product, so I'll need a product rule. So I'm going to have e to the negative x, the second, multiplied by the derivative of x squared, which is 2x, and then I'll have x squared multiplied by the derivative of e to the negative x. E to a power is its own derivative, but if the power is anything but plain old x, you need a chain rule. So I'm going to have to chain out the derivative of negative x, which is -1, and I'm just going to switch that to a minus to make sure I don't make any mistakes with that negative sign. I now need to think about when is it 0 and when is it undefined. And the undefined question gets the same answer as before. I have this combination of like a quadratic and an exponential, and both of those have all real numbers as their domain. So I don't need to write all real numbers. I need to say no, it's never undefined. No or NA, whatever you want, but just write it down, get in the habit of writing it down so that you get in the habit of doing it. If I want to solve with this mess equal to 0, what you're going to want to try and do a lot, even when it's weird and messy, is factor. And in this one, even though it looks scary, there's a greatest common factor. So I can factor out the e to the negative x, and I can also factor out an x. And that just leaves me with a 2 and a minus x. Once you get it factored and equal to 0, you can set each factor equal to 0, and we can even break this into 3 if you want to. I think that might be the easiest for people to make sense of. So 1, if x equals 0, the whole thing is 0. 2, if e to the negative x equals 0, the whole thing is 0. But as we talked about up above, e to the x is never 0, and 1 over to the e to the x even more can't be 0. I don't know if there's an even more, but also can't be 0. So we end up throwing that away. If you don't spot it immediately, your next step would be to take the log of both sides. So notice you get the natural log of 0, and that is not allowed. You can't take the log of 0 or negative numbers. So hopefully at some point your log memory kicks in and you recognize that you have a problem. And then the last one, 2 minus x equals 0 if x is 2. So we have critical values at x equals 0 or 2, two critical values. We now want to try both a first and second derivative test just so you can see and compare and contrast. The first derivative test really from there just requires a sign chart. So I want 0 and 2 on my sign chart for sure. And that's when the derivative is 0. So I think I'll test -1, 1, and 3 to get all 3 segments. If I test -1, I'm going to use my factored method again. I'm going to look at this. So when I plug in -1, x is -1, so I get a negative number out in front. And again, if you like it, you can write the 1. And then I get e to the 1, right, negative x in the exponent. So when we plug in -1, it becomes +1. So just e, which is positive. So I'm saying positive when I'm trying to write. So I have a negative and a positive so far. And then I have 2 minus -1, which is 3, which is also positive. So negative and 2 positive ends up being negative since we're multiplying. When I plug in 1, so that was -1. When I plug in 1, I get a positive 1 times e to the -1, which is still positive. E to any power is positive. And then a 2 minus 1, which is also positive. So that's a plus. And then when I plug in 3, I get 3 times e to the -3, and I'm kind of swapping back and forth on how I write this so you can see different examples. I'm fine with any of these, and hopefully I'm not confusing you. And then 2 minus 3 is -1, so that ends up being a negative number. -3 over e cubed is negative. Okay, so I'm visualizing now that my function was, here I'll use a different color, decreasing, and then flat, and then increasing, and then flat, and then decreasing. This isn't a polynomial, so it probably doesn't look just like that, but that's kind of the beginnings of shapes in terms of thinking about maxes and mins. So I think I have a local min at x equals 0 and a local max at x equals 2. So min at x equals 0, max at x equals 2. Okay, so that's it. That's all I need to do, but I am going to do a second derivative test as well, just so you can see it. So I would still have to do part A, but if I want to use second derivatives, I would then need to take h double prime, which is going to be a little bit messy. So if I'm given a choice, I might not choose second derivative test here, but it's not terrible. I'm going to have to do double product rules. So I see a 2x times e to the -x. So I'll need an e to the -x times the derivative of 2x, which is just 2. And then a 2x times the derivative of e to the -x, which e to the -x is its own derivative, and then I have to chain out a -1 from that -x in the exponent. Let's see if I can fit this. And then I have, this is how I'm going to think about it. I'm going to think about it as plus, and then I'm going to mentally hook that negative to the x squared, because otherwise you'll have to distribute it through, and it's really easy to forget. So my first function is -x squared, and my second function is e to the -x. Okay, so I have an e to the -x times the derivative of -x squared, which is -2x. This is going to be really scrunched. Hold on, let's write that e smaller. E to the -x. And then I have a -x squared times the derivative of e to the -x, which is e to the -x times -1. So I'll make that a plus. And I actually get to combine just a little bit. So this is h double prime 2e to the -x minus 4x e to the -x plus x squared e to the -x. And now what I want to do for a second derivative test is not make a sign chart. It's to say, okay, at x equals 0 and x equals 2, I have flat spots at x equals 0 or 2. If there's a corner, this doesn't work. We have to use first derivatives, but if they're flat spots, we can do it. I want to know right at that horizontal tangent line, is the graph bending up or is the graph, oh, I drew that one funny, bending down? And that'll tell me if it's a max or min. So it's a combination of flat spot and concavity. So if I want to know right at 0, I plug 0 into h double prime, and the same thing for 2. Sorry if you heard that squeak, it's my dog having dreams. Okay, so at 0, when I plug that in, I get 2 e to the 0, e to the 0 is 1, minus 4 times 0 times e to the 0, that's 0, plus 0 squared times e to the 0, that's 0. So just 2, that one actually worked out nicely, which is positive. So I'm picturing the concave up shape, concave up, which is a minimum. And that should agree with what I said before. I think it does. And that's my other dog getting bored. Sorry for all the animal sounds. Okay, when I plug in 2, I get 2e to the -2, which is 2 over e squared. And then I get minus 8e to the -2, so minus 8 over e squared. And then 2 squared, so plus 4e to the -2. You don't have to rewrite it as fractions. We'd be able to sort this out if it was all times e to the -2, but I kind of like it. It's common denominator, so I end up with 2 minus 8 plus 4, which is negative 2 over e squared, which is negative, which means that my graph is concave down and I have a max, which again agrees with what I said before. So it's not that we're expecting a different answer. There's a problem if we get a different answer. It's just that this is another way to do it. So in this problem, given the choice, I think I like my first derivative test. In other problems with functions that have a little bit neater second derivative, the second derivative test can be really slick. It's really nice if your second derivative isn't messy. Okay, and then the other one that we talked about up above, but we haven't done it all the way from scratch yet, to find inflection points. And this is where it can kind of start to get confusing. You have to keep track of a first derivative test, a second derivative test, and how to find inflection points, which is similar but different. So to find inflection points, we set h double prime equal to 0, and then we test. So this will be an f double prime sign chart. So you can see we have sign charts for 2 of the 3 tests. We need h double prime for 2 of the 3 tests. We set a lot of different things equal to 0. So really work on just keeping track of what to do in what situation. Each of these on its own is not very hard, but keeping track of all 3 can get a little tricky. Okay, so I'm going to go back to, hold on, where is it? This. And I know I want to set it equal to 0, so I'm actually going to factor while I'm at it. I'm going to take out an e to the negative x, and I'm left with a 2, a minus 4x, and a plus x squared, and that's equal to 0. So e to the negative x never equals 0, so we can throw that away. But 2 minus 4x plus x squared can equal 0. And it doesn't look factorable, so you can use a quadratic formula. I'm actually feeling like completing the square today, so I'm going to remind you how to do that. But absolutely use quadratic formula if you like it better. To complete the square, we want to kind of mentally group up the x squared and the 4x, and then we're just going to leave the 2 out until we decide what to do with it. You need a coefficient of 1 on your x squared. So if there was something in front of the x squared, I'd factor it out of those parentheses I added, but I don't have that here. And then the magic trick is you take your b value and you divide it by 2 and then you square it. So I get negative 2 squared, which is 4. And then if you're going to add 4, you also have to subtract 4. So I end up with x minus 2 squared. That's the whole point, is it makes a perfect square. And then minus 2. So we can add the 2 to the other side. X minus 2 squared. And then we can square root both sides. X minus 2 equals plus or minus the square root of 2, which means x equals 2 plus or minus the square root of 2. And then I'm kind of scrunched here, but I think I can fit it. I want to, it's easy to think you're all done there, and you probably have found the x-coordinates of your inflection points, but we're not quite all done. We need to test and make sure the concavity really changed. The definition of inflection point is not the second derivative equals 0, it's the second derivative changes sign. So we're going to mark off the 2 minus root 2, and the 2 plus root 2, and we're going to say the second derivative, h double prime, is 0. So we need to plug in one number in between, which is actually easier than you might think at first. 2 is definitely in the middle. We're subtracting and adding to 2, so 2 is right smack in the middle. When I do that, I'm going to go back to right here, and I'm going to say the e to the negative x is always positive. When I plug 2 into the quadratic, I get 2 minus 8 plus 4, so 6 minus 8. Ooh, you know what? I think I've already done some of this work. We did this up above. So if you're paying attention, right here, I did some of this. I got a negative number. So we can say what we got basically was a positive and a negative, but we can say that the second derivative is negative. We also plugged in 0, so we can use that without doing new work. And at 0, so that's going to be over here. You can double check 2 minus root 2 is positive still, but at 0, we got a positive number. So really, all I need to test is something bigger. Root 2, I think that's like 1.4-ish. So 4 would probably be big enough. If in doubt at all, just pick something even a little bigger. We could pick 6, and we could say, okay, the E part is always positive. Then I'm back to looking at this right here. 2 minus, I'm going to write it out, 2 minus, we're plugging in 6, 24 plus 36. So 38 minus 24, that's positive. So this goes back to positive. So it did in fact switch concave up to concave down at 0. I'm sorry, at 2 minus root 2, and concave down to concave up at 2 plus root 2. So they are both inflection points. Sometimes in my open math, it'll want you to get a y value, and I actually probably want that for sketching the graph. But for skills tests and things, usually I just ask for the x value. So just pay attention to what it says, if it wants coordinates or if it wants an x value. So just for down below, I have already plugged these in. For the 2 plus root 2, and in fact, I'll convert that to a decimal. I got 0.384 roughly. We'll leave it at 0.38. And the 2 plus root 2 is 3.4 or 1-ish. And then for the 2 minus root 2, 2 minus root 2 itself is about 0.59. I'm plugging this into the original function. So I want to know the point on the original function where the concavity changes. The y value I got was 0.19 roughly. Okay, so if I'm going to graph this thing, most of the interesting stuff was at the positive side of the y-axis. Okay, so about 0.6, and then it's just above the axis, and then about 3.4, and it's a little higher than that. Okay, those are inflection points. I know I had a max at x equals 0. Let's remember the equation was x squared e to the negative x. So when I plug 0 into that, it's at 0. And I'm sorry, I think I just said max. That's a minimum. This is an inflection point. This is an inflection point. And then the other max was at x equals 2. And when I plugged that back in, I got about 0.54. Okay, so that was the max. So we'll say this is about 0.5. Just above that. So about here is my max. And then I actually know even more than that. I have sign charts. So up above, I know that the graph decreases. So it's decreasing to the minimum, and then it's increasing everywhere in here, and then it decreases forever after this. I can also look at this formula and think about global behavior. That can be really helpful. If you plug in big negative numbers, when I square them, I get really big positive numbers from the x squared. And when I plug in big negative numbers here, they become positive in the exponent. So raising e to big powers gives me big positive. So I'm headed to big positive on the left. If I plug in positive numbers, big positive, that x squared is getting big. But I'm basically getting x squared over e to the x. So the top is getting big and the bottom is getting big. And you can just plug in some numbers to convince yourself if you want. But exponential always grows faster than any sort of power. So this thing is actually headed to 0. The bottom is getting way bigger. So this has a horizontal asymptote at 0. And then we even know a little bit about concavity. We made a concavity sign chart right here. We know the graph starts concave up. So we're concave up decreasing. And then it's concave up all the way to the inflection point. So still concave up, but then it switches to concave down, still increasing. So now I'm bending down. And then it switches to decreasing concave down. And then it stays decreasing but switches to concave up as it approaches the asymptote. So this is tricky, and truthfully, we would use technology to graph a lot of these hard things, but I want you to practice a little bit and think about it just because it helps put all these pieces together. It's a good challenge. So, long video, I'm sorry for that. Thank you for watching.